Next chapter, we've been dealing with, so far what we've done is we've done kinematics, and that gave us our three general equations, that my change in position is going to equal a velocity, my initial velocity times time, plus 1/2 acceleration times time squared. I've got velocity final is equal to velocity initial plus my acceleration times time. I have velocity final squared is equal to velocity initial squared plus 2 times my acceleration times my change in position. And from this, if I have a constant velocity or a constant acceleration, we can get rid of and we can get our change in position is equal to my initial velocity times time. The other thing that we've done so far is our trigonometry, where we have our angle, and we can do our sine, cosine, and all of those lovelies, which gives us a lot of our vector notation. We've talked about vectors having direction and magnitude. We've talked about independent things that happen independently. We've done our summation of forces is equal to mass times acceleration. We've also done our universal gravitational one is equal to this big G mass 1 mass 2 divided by r squared. So far that's kind of our toolkit. And you go back and you think about it and you go, oh my gosh, that's not a whole lot. But we've done a whole lot. We've done projectile motion, we've done calculating whether or not somebody's going to make a field goal, we've calculated whether or not I can block the shot in the soccer goal, we've done a whole heck of a lot of different things with just this sets of information. Now, I'm about to give you my favoritist definition of all. And I'm going to promise you when I give you my favoritist definition, I might as well be speaking Klingon. Although there's probably a Trekkie in here that actually can speak Klingon. Or I'm going to be speaking Elvish. Some of you might be Tolkien fans and can speak Elvish. Okay? But I'm about to give you a definition. And I know I've just given you a definition that all of you are going, okay, so you just wrote the words down, but that doesn't mean a thing to me. And that is true. But it is a very simple definition, it's a very elegant definition, and we're going to get to understand what those words actually mean. So, let's look at our ball situation. We have been doing this now. We have been dropping a ball from a height for 7 weeks. And one of the Pivot laboratories said, we didn't care if this had a mass of 16 kilograms. We didn't care if it had a mass of 8 kilograms. We didn't care if it had a mass of 0.5 kilograms. Or even, we'll go ahead and do the 0.005 kilograms. Didn't matter. Didn't have, it's like, didn't matter. Because we knew we could deal with the time, we could use these kinematic equations. There is no mass in those kinematic equations. Things that did matter were, we had vectors. We had to worry about direction. Because if I set this ball off at an angle, we were going to get projectile motion. But the time that it took this one to fall that same distance was going to be the same. Now if we did this one right here, if we had it roll off the edge and we had it land over here, the time that it took both of those to fall is going to be the same. So we get some interesting things that are happening. But let's look at this a little differently. Let's look at it a little differently. Let's think of an old-timey well. And we've got our rope coming off our old-timey well. And we've got our bucket on our old-timey well. So we've got this, right? So we're in our old-timey well. Give our picture here. And we've got our little crank. I feel like being a relatively decent artiste today. So we've got our old-timey well, and our well is now filled with water. Now one of the things I have to do is I have to have a break over here, otherwise we know what's going to happen to the well, or the bucket, right? What's going to happen to the bucket? The bucket's going to fall back down into the well. Now one of the things I had to do to get the bucket up there is I had to crank on the crank. Alright, I had to crank on the crank to get the bucket up there. Now if I go ahead and fill this water bucket, and then I let it go, this is going to spin around. And I can make that do something for me. So we've all seen this situation. So I've got my big water wheel here, right? I got my big water wheel here. And I have my water coming in, and it's going to hit this, and it's going to cause my wheel to turn. And I can have a big shaft here, and I can make that wheel turn. This is the idea that we call work. We can actually have this water do something for us, just like this bucket do something for us. So what we've done by cranking this up is we've stored energy in here. We have created a way to store something that we're going to call energy that we can actually use to do something. Give us this idea of work. So let's look at what we've done. So if I'm doing my bucket situation, so we're going to start with our bucket. And we're starting at the ground. And I'm going to lift my bucket to a designated height. A couple things that we've had in this picture. One is I've applied a force. I've applied a force. I have a change in position, which is also a vector. So I have two vector things that are happening here. I've applied a force, I have I'm moving it in a height, and this is going to give me something that we're going to call work. Now what's weird about this is I'm going to give you this mathematical situation. I have a vector, and I'm going to do a dot, and I've got this. We're going to call this a dot product. We're going to call that a dot product, but this really is something we're going to call a scalar product. Now work, now let's look at something a little differently here. So if I'm doing, we'll play with the grocery cart, because most of us have experience with a grocery cart. I'm going to apply a force to the handle. Now I can apply a force this way, I can apply a force that way, I can apply a force that way, right? We can apply a force on that grocery handle all kinds of different ways. And one of the things that we just saw that if I had my suitcase and I'm applying the force on my suitcase, this was our 36 newtons, only this force, this one right here, was helping me do anything. The bigger bang for my buck to move my cart is if I'm applying a force that's directly in line with the direction that I want to move it. If I'm applying a force like this is actually hurting me. Because guess what's happening? I got my weight, I'm adding a new force, and that's going to be dealing with my normal force. And we all know my force due to friction is the coefficient of friction times my normal force. So if I'm pushing down on the handle, I'm creating more friction. I'm going to have to do more. I'm going to have to put more energy into the system. I'm not getting a good bang for my buck. I'm not getting anything good for that. And it's like, and that's not, all I'm doing, and then if I got the wobbly cart, or I've got the cart with the flat roller on there, I'm doing a heck of a lot more. I have to do a heck of a lot more effort to get my cart to move the other direction. So my work is going to be maximum if we're drawing our picture here and we're trying to go in this direction, this is the direction I want to go, that angle, if that cosine of that angle is equal to 1. It's going to be maximum when I'm at that angle equal to 1. So it'll be maximum when the cosine of the angle is equal to 1, and that means my angle is equal to 0 degrees. Or, thinking of it in terms without putting in numbers, the work's going to be maximum when the direction of the vector that I'm applying is in the same direction as the distance that I want to go. And for you math geeks, that's saying that I dot I is equal to 1, J dot J is equal to 1, and K dot K is equal to 1. So if you want to play the math geeky game, you can. But fundamentally what this is saying is as long as I'm applying the force in the same direction that I want to go, I'm getting the maximum work. I'm getting the maximum work. So, let's think about our bucket situation. So we've got our bucket situation. And we're raising our bucket. And the force that I have to do has to overcome the weight. The force that I apply has to overcome the weight. So that works. So that's all good. Here's the height that I got to do. And we just said that the work that I just did is going to equal the force times this, which, if I write it all out, is going to be mgh, cosine of my angle, but my angle is going to be 1 because I'm applying the force in the exact same direction. And now the work that I just did is mgh. Now that's a magnitude, but here's the fun part. I no longer have a vector. Vectors went away. They went poof. I just have a number. Now, let's think about this for a second. I put in work, but This could also be named something special because once I have this up here, it now has potential energy. Because once my bucket is up at a height, so now my bucket is up here, and right now I'm holding it there, and we've raised it from here to here. This now, the work that I put into the system, is currently stored. So my work can also be equal to, we'll do it this way, we'll just keep writing out the words, my change in potential energy. And we're starting to develop work energy theorems. So, let's talk about that for a second. We're starting to develop work energy theorems. So let's go back to the history. Can't teach physics is a natural philosophy, right? I have a degree in philosophy. And you're all going, what? Physics is, it's hard science. It's the scary stuff. No, physics is a natural philosophy because we have to do all these thought experiments. Okay, we have to do these thought experiments. We're trying to explain how the world works. And we're trying to understand the rules. That's what physicists are doing, trying to understand the rules. So we're trying to understand these rules. And one of the things about these rules is, okay, I just did work. I did something physical. I did work. I picked up my bucket. I got it up there. And now as long as I'm holding it there, I've stored energy because all of a sudden when I let it go, it's going to do something. And so we're at these work energy theorems. Now, think about this for a second. So Newton gives us Newton's laws way back when. And actually, it's really not that far back. It's kind of scary how not far back it is. And then we get to the 1800s, and in the 1800s, we start having these discussions about work and energy. We start looking at this. We're building steam engines. And we're building steam engines, and that's a big deal. So we're actually trying to do these things. We're trying to improve upon the situation of my good old water wheel. The water wheel gives us the Industrial Revolution, which starts in the early 1800s, and we want to figure this out. We want to compare these things. We got mine ponies doing stuff for us. We got all this stuff. And now we're going to sit there. How do we actually do these calculations? And how do we actually figure out what we got to put into the system? And how do we compare? A lot of this comes out of the idea of how we compare things. Can you compare a steam engine to a mine pony? Okay, yeah, we can do that, but how do you do that on an equal basis? So, good old J.J. Thomson, which is Lord Kelvin, he's pondering this question, and we got Watt over in England, he's pondering these questions, and Lord Kelvin says, wait a second. Energy and work are the same thing. And we get this idea of conservation of energy. So while we even haven't stated it so far, one of the things that we know we conserve is if I start out with 10 billiard balls, and I do something to those 10 billiard balls, I still got 10 billiard balls. So we have this idea of conservation of mass. But now I've got conservation of energy. So Lord Kelvin writes this lovely paper sends it to the German Academy of Sciences, which is where you sent those kinds of things back then, and the German Academy of Science laughed him out of the room. Said, no, that can't be right. And the German Academy of Sciences laughed him out of the room. Well, Lord Kelvin has the last laugh. Guess what? We have conservation of energy. And if we don't have this principle of conservation of energy, we are doomed. We are doomed. So we do have conservation of energy. Energy cannot be created nor destroyed. We just change forms. So now I've put work into the system, and my work is now equal to my change in potential energy, and it doesn't matter. So let's think about what we're doing here. It does not matter. Does not matter at all. So if I have a mountain, here's my mountain. Okay, there's my mountain, and I'm looking at my change in height. Okay, I'm looking at my change in height. I'm starting down here at h is equal to 0. I'm going to end up at here at h is equal to max. My change in potential energy is going to be mass times gravity times my change in height. It doesn't care if I do it this way or I do it this way. The world doesn't care. So how I lift my ball from the surface of the earth to at some height above the earth, it doesn't care. I have a change in potential energy. I have a change in potential energy. We call those state functions. It only cares about where I start and where I finish. That's all I care about. So I have a change in potential energy. Now, our book is going to use this lovely letter U. When I'm writing my notes, I won't use U. Okay? I won't use U because U is kind of like whatever. It doesn't resonate with me. I'm going to use PE, potential energy, so that we can keep track of what we're doing. Okay, so let's go back to our ball drop. So we're going back to our ball drop, and we've got our ball, and it's going to fall due to gravity. But now we know at the top here, the energy is all stored. And we know what that storage is. That's now the potential energy. And we now have my potential energy is equal to something we can actually deal with, mgh. So if this is the height of my building, I can look at the potential energy of that material. Pretty cool. And I don't have to worry about vectors anymore. So that's pretty cool too. Now, we all know what's going to happen because what do we have here at the top? We have my velocity is equal to 0. If I'm just going to do a ball drop. But when I get to the bottom, my potential energy at the bottom, because now my change in height is equal to 0, my potential energy at the bottom is equal to 0. But one of the things that we know is happening down here is it's moving. Okay? It's moving. And we all know, because we've had it happen to us, right? You all know that if I get hit by a moving baseball, it's going to hurt. If I get hit by a moving soccer ball, it's likely to hurt. So we know intuitively that there's a change in energy here, because remember, energy is the ability to do work. And we already saw that to go from here to here, I had to do work. So to go from here to here, I've got to do work too. But now my work is a change in kinetic energy. And you can go into your book and look at the derivation, but we're going to make life easy on ourselves. And we're going to define my change in kinetic energy as 1/2 the mass times the velocity squared. 1/2 the mass times velocity squared. That's my change in potential kinetic energy. And again, my kinetic energy at the start is 0. My kinetic energy at the bottom now is 1/2 mass times my final velocity squared. And that's my kinetic energy. So work can also be the change in kinetic energy. Another part of the work energy theorem. Another part of the work energy theorem. So basically what we're saying is work is going to equal a change in energy. And we can look at these as conservative energies plus non-conservative energies. And you're going, uh-oh, wait a second. You just told me that the physicists say that energy is neither created nor destroyed, it's just going to change forms, and now you're telling me that I'm not going to have conservative energy. Well, that's because friction isn't our friend. Friction is our friend, but it's not our friend. Because what's going to happen here is if I am rolling a box across a surface, I'm putting in a force and we're going to move at a distance, I've done work. But we also know, because if I rub my hands together, I'm going to generate heat. So let's look at other forms of energy. So we just looked at potential energy. We've looked at kinetic energy. But there are other energies. Heat being one of them. Light being one of them. Sound is one. I have electrical potential. But what happens here is if I am dropping my ball, okay, I'm dropping the ball from a height and it comes down, and if I drop it from a big enough height, we know we have air resistance. And air resistance is going to heat up the ball. So some of the energy of motion, which gives us the kinetic theory of temperature, if I'm moving around the molecules, there's going to be friction and the temperature is going to go up. In fact, what we do know is we can do this, and there's an actual experiment that you can do this, is if I have a fan or a mixer and I am spinning my mixer, the temperature, I'm putting work into the system and the temperature is going to rise. The temperature is going to rise. So if I put work into my system, the temperature is going to rise, I generate heat. The problem with heat is I can't go back and capture it. It's going to leak out of the system. So if we have the little kid that's going up the slide, right, and on a cold day, so let's say on a day like this morning, and we're going into our little slide here, the little kiddo is going to do work to get up to the top. Then I'm going to have potential energy at the top. And the kiddo is going to slide down to the bottom, and I'm going to have kinetic energy at the bottom. And if I do that enough times, what do we know about the slide? The slide is going to warm up. The slide is going to warm up, and I'm going to get a little bit of heat. And that little bit of heat is going to go to the atmosphere, and I'm going to lose it out of the system. Now, if I do it one time, if we've done it one time, I'm not, well, you know, that little bit of heat is so small, I'm probably not going to see it in my numbers. Because my potential energy is going to be equal to my kinetic energy, which is equal to the work, and these are conservative values. But I'm going to generate a little bit of heat that's going to go out there, and that's a non-conservative. Because I can't go back and get it. And because, and this is one of those things, we probably will not have time at the end of the semester to do thermodynamics. And this gives us our problem in the second law of thermodynamics. And the second law of thermodynamics sums up as Mother Nature isn't fair. Over the course of one cycle here, and for what we will actually end up doing in a lot of stuff, we'll be able to see that we have conservation of energy. If I use something that doesn't have a whole lot of friction, I get conservation of energy and it works out really great. But Mother Nature isn't fair and I lose this heat. And the second law of thermodynamics says I can't put 100% of work into my system. I'm going to give up something to the environment. So while energy is still conserved, and this is why the German Academy of Science looked at Lord Kelvin and says, you're full of it, because they're thinking about this heat aspect. They're thinking about these non-conservative items. So my work energy theorems are going to allow us to look at conservation of energy. So I promise we get back to the ball drum. So let's look at the ball drum. So I have my ball, and we're going to drop. And we want to know, what we want to know is the velocity final at the bottom. And we know this is the height of the building. We've got our acceleration due to gravity. And if I do it with our kinematics, so this is our kinematics. The kinematics, right? We know that the the final velocity squared is equal to the initial velocity squared plus 2 times my acceleration times my change in position. So if I write this out, I get final velocity squared is equal to initial velocity squared minus 2 times my acceleration due to gravity times my height. Now we're in the y direction, so life is good, right? And my change in height, it's got to be negative, so I'm going to put my negative in there because otherwise I'm going to have a real problem. So my final velocity squared is equal to 2g h. And my final velocity is equal to the square root 2gh. That's our kinematics way of dealing with our ball drop. Alright, well, let's look at it the energy way. At the top, we have potential energy. So at the top, now I've got potential energy at the top. I have kinetic energy at the top. But my kinetic energy at the top is 0 because my velocity at the top is 0. Then at the bottom, I have potential energy at the bottom. Well, I have no height, so that's 0, but now I have kinetic energy at the bottom. My kinetic energy at the bottom is going to equal my 1/2 mass times velocity final squared. Kinetic energy at the top is equal to mgh. So total energy at the top is got to equal total energy at the bottom. Because I have conservation of energy. And we're only doing one cycle, so I'm going to neglect air resistance, so I'm going to say it's not going to heat up and we're going to be okay. So I get potential energy at the top plus the kinetic energy at the top is equal to total or potential energy at the bottom plus kinetic energy at the bottom. Well, this was equal to 0. This one was equal to 0. This is mgh. This is 1/2 mv squared. Masses cancel. I get 2gh is equal to v squared. V is equal to the square root of 2gh. I get to the exact same spot. I get to the exact same spot. So, if we go back here now, we can add this idea: energy is the ability to do work. Energy is conserved. We get work is equal to my dot product of this, which is going to be FD cosine of the angle. We get potential energy is equal to mgh, and we're actually going to call that gravitational potential energy. And I get kinetic energy is equal to 1/2 mv squared. And these things right here have just now dramatically added to our toolkit. Dramatically added to our toolkit. Questions? Making sure there's nothing in the chat here. Get there. Uh-oh. Looks like I was one of the ones that dropped from the meeting, so, because it said it couldn't connect. So if you have a question, my Zoom folks, you better need to go off mute, because I'm going to stop there. We will start playing with more of this on Wednesday.